Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. A reminder that if you do enjoy the show, do please consider supporting us through buying me a coffee. It really helps us to keep making the show. So yeah, please do consider supporting us. Today, I'm joined by Jinkun Geng, who will be telling us everything we need to know about Nezha, deployable and high-performance consensus using synchronized clocks. Jinkun is a PhD student at Stanford University. Jinkun, welcome to the show.
Yeah, thanks for the invitation, Jack.
Great stuff. So let's jump straight in then. So can you maybe tell us a little bit more about yourself and how you became interested in databases, distributed systems, and all the cool research that you do?
Yeah, cool. Sure. So my name is Jinkun Geng. So I'm now a fifth-year PhD student in the CS department of Stanford University. So my research direction is the networking system. So more specifically, my current research project focusing on high-performance distributed protocols, including consensus protocols and the concurrency control protocols. So before I joined Stanford in 2019, I completed my undergraduate study and my master's study both in China. So I completed my undergraduate study in Beihang University, and then I entered Tsinghua University to obtain my master's degree. So regarding my research career, I think I can divide that into two parts. So the first part is before my PhD. So I conduct the research in Tsinghua University, advised by Professor Dan Li. So at that time, I was doing high performance networking, which means I use DPDK RDMA to accelerate the communication in distributed systems. So further, based on that, we can continue to bring performance improvement on distributed applications, such as distributed machine learning applications. And that is what I was doing in my master. And when I came to Stanford, I finally found my current supervisors. So I joined the group of Professor Balaji Prabhakar. And Balaji is my primary advisor. And at the meantime, I'm also co-advised by Professor Mendo Rosblum and also Professor Anirudh Subramanian. So Mendo is another professor in Stanford, and Anirudh is a professor in New York University. So in our current group, the general direction is called time-sensitive networks. So the motivation for this general direction is like this. So dating back to decades ago, such as 10 years or 20 years ago, at that time, clock synchronization has not been a mature technique. So the clock synchronization error can be quite bad, dating back to 20 years ago. The different nodes can even reach the error bound of 100 milliseconds. So for the early researchers in distributed systems, they cannot make strong assumptions of the clock synchronization. So, but in the recent years, especially in the past 3 to 5 years, we have seen that clock synchronization is developing very fast, and the traditional protocol like NTP has improved the synchronization accuracy to a greater amount. And for the and some new clock synchronization protocols have also been proposed, like the synchronization algorithm we have used in Nezha protocol, which is called Huygens, which is developed by another senior lab mate in our group. So with the new synchronization algorithm, we can reach the clock synchronization accuracy at nanosecond level. So in that way, with this new powerful tool, we come to ask whether we can review and even revolutionize the previous distributed system research and achieve much better performance. And the consensus protocol is one such scenario.
Fantastic. That's a great mission statement for what your lab are doing there. I mean, yeah, like you say, it's a different ball game from 20 years ago, right? Like the underlying assumptions have changed. We've got better hardware. So, well, how does that change the state of play? So, yeah, I guess that's what we're going to be talking about today. So, in some more depth. So, cool. So, let's start off with a little bit more background for the listening. So, before we dig into all the nitty gritty and everything, can you tell us more about kind of consensus protocols generally? What are they, and why do we need them?
Yeah, okay. So, actually consensus protocol is nowadays widely applied in many distributed systems because distributed systems require fault tolerance. So consensus protocols help the system, consensus protocols provide the fault tolerance for the systems. So it can ensure the service availability for the distributed systems. When the one server fails, You just need to use the other servers to replace the failed ones, and it can resume the service for the systems. So simply speaking, the consensus protocols can be defined in a scenario with multiple servers. So the protocol needs to coordinate the multiple servers so that they can reach an agreement on a single data value. So this is commonly known as a single decree Paxos, or you can call that a single decree consensus, because Paxos has already become the synonym of consensus. But of course, in the practical cases, the single decree consensus is not sufficient for the applications. So in many practical cases, we can make abstraction of the application's execution. We represent the execution history of the application as an ordered log list. So it becomes the responsibility of the consensus protocol to make sure that every server has the same ordered log list. So in that way, when the active server fails, we just need to use another server which has the same ordered log list to replace that. By re-executing the log list, we can recover the same application state, and then we can resume the service.
Fantastic. It's a great description of what consensus was. I mean, I personally work with one every day. So we have Raft at work. So I've had fun with that quite a lot of time. But cool, right? Anyway, I'm getting sidetracked. So let me keep on focus. So of course, you mentioned there that Paxos is sort of like kind of almost a synonym for consensus protocols. I know there's a host of other ones like Raft out there, but what are the current problems with what are the problems with the current state of art of consensus protocols, and why does we need to sort of have a new one, right? Like what's the motivation here, the problems, and then I guess leading into the motivation for your work?
Yeah. I think based on my understanding, I think for the state of art for the existing consensus protocols, the drawbacks can be summarized into 2 dimensions. So the first dimension is performance, and the second dimension is deployability. As you mentioned, for the traditional protocols like MultiPaxos and like Raft, when they are designing the protocols, they cannot make strong assumptions. So for these protocols, of course, with many, they do not have strong assumptions, so they can be deployed everywhere. But the performance is not very good. And for these protocols, they usually suffer from the throughput bottleneck, and also the commit latency can be very long. So that will become the bottleneck for the system and applications running on top of them. So these drawbacks of the traditional protocols have already been realized by some recent works. So for some recent protocols like NOPaxos and Speculative Paxos, they are trying to achieve high performance. So in order to do that, they decide to use some network support, such as the program switches, such as SDN control. But in that case, it introduces another problem, which is the deployability. Because we know in the public cloud, which is the general environment for many systems and applications, we do not have the support for, we do not have such strong support. From the perspective of the cloud tenant, the network is just like a black box. So you cannot use program switches or SDN control. So in that way, the high performance protocols developed in the recent years cannot be easily deployed in public cloud. So that is why it motivates us to design a new protocol. We hope that we can achieve both high performance and deployability so that we can provide benefit to the cloud systems and applications.
That's fantastic. I mean, I've always had this sort of, whenever I come across a cool paper that's used some sort of modern hardware that's cutting edge, and it says, yeah, look how fast we can make this system go using this hardware, or we can solve these problems using this hardware, and it goes really fast. Is this what you mentioned there, this deployability of that? Like, that's not generally available in the public cloud, and therefore it's kind of, well, it's not irrelevant, but like I can't use that in a day for like day to day because not everyone has access to it, right? So I think it's great to factor that sort of dimension into your design process. So I guess with these sort of 2 dimensions in mind, then give us the elevator pitch for Nezha, and I think I'm pronouncing it right. Is it Nezha?
Nezha, yeah.
Nezha, okay. What does it mean? What does it mean?
Nezha actually it comes from Nezha is the name of a Chinese legendary figure. So for Nezha, actually, cool. This figure has 3 heads and 6 arms. So you can imagine that if you cut down one head, this guy is still alive. So it has much more,
okay, cool.
It has a stronger fault tolerance.
I get it. I get it. That's a great name. That's a great name. Cool. Well, yeah, so give us the elevator pitch then. Well, how are we going to achieve these two goals?
I think there are three design pillars. I think there are three pillars in the Nezha design. The first aspect, of course, is clock synchronization. So let's first think about this question: why does clock synchronization accelerate the consensus protocols? So essentially, consensus protocols are trying to establish the agreement of one ordered log list. So if you can imagine that if you have multiple replicas and you have many clients, imagine that each request is multicast to every replicas, and imagine that each request will arrive at the replica in the same order. So in that way, these replicas will establish the same ordered log list by nature. So we do not, even without coordination. This is the ideal case, but this does not always happen. This can hardly happen actually in the public cloud, because in the public cloud, we have observed that message reordering occurs very frequently. So in that way, if we can reduce the message reordering in the network, then we should be able to accelerate the consensus protocols. This design principle has already been realized by the existing works, like what I mentioned, such as NOPaxos and Speculative Paxos. So they decide to resort to the networking support like SDN control to control the networking transmission in order to reduce the message reordering. But also, as I mentioned, this network support is not available in the public cloud, but clock synchronization is already available in the public cloud. So we decided that we can use clock synchronization to reduce the message reordering so that we can accelerate the consensus. So motivated by that, we have first developed a primitive which is called deadline order multicast primitive, and we can talk about that later. And based on DOM primitive, we continue to develop now Nezha protocol to achieve high performance. So this is the first aspect I want to highlight. So the second aspect I want to say is the speculative design, which we included in the Nezha protocol. So if we take a review of the traditional protocols like MultiPaxos and Raft, we can see that for these protocols, they ask the leader to execute the request after the leader has confirmed that the request has been replicated to a majority of replicas. So the confirmation operation is also known as the quorum check, which means that in the traditional protocols like MultiPaxos and Raft, only after the quorum check is completed, then the execution can be done. So this actually prolongs the commit workflow. So we don't want that. So in our design, we just ask the leader aggressively execute the request. So that means it is no longer the responsibility of the leader to do the quorum check. And we have another entity to help the protocol do the quorum check to decide whether this request is committed or not. So this is the second aspect, the speculative execution. And following that, the third aspect is also related to the second one. So which means in our protocol, we have extracted a stateless proxy design. So the proxy becomes an important component. It helps us to do the request multicast and help us to do the quorum check. So in that way, for these heavy operations, which are used to be done by the leader, we have offloaded them into the proxy. So in that way, the leader's bottleneck becomes much reduced. And because the proxy is stateless, we can scale up and down the number of the proxies based on the workload. So if your workload is heavy, you can deploy more proxies. Otherwise, you just need to reduce the number of proxies. So because the proxy is stateless, the failure of the proxy does not affect the correctness of the protocol. And because it is scalable, it helps us to reduce much of the bottleneck at the leader. And additionally, because the proxy also serves as a middleware, it serves as an adapter for us to migrate the distributed system from legacy protocols to Nezha. For example, many systems are running on top of MultiPaxos and Raft. By just implementing an adapter of the proxy, we can easily migrate the distributed system from Raft and MultiPaxos to Nezha, so that they can also enjoy the high performance provided by our protocol.
Fantastic. So just to recap there briefly, the three pillars of Nezha there are the deadline ordered multicast, which is helping us with our. I did have a question on that actually. before we continue is you mentioned that in the public cloud, it's been observed that message reordering happens frequently. Do you have any sort of like numbers with that, like as a rough guideline of how frequent we're talking?
Oh, yes. So in our paper, we have included that number. We have included that experiment. So based on now, first we define a metric which is called reordering score, and to measure the frequency of the reordering. And based on our measurement, we have found that so long as you have multiple senders and so long as the sending rate increases, you will reach a very, very high reordering score, which can be 20% to 40% of reordering, which can be 20% to 40%. So that indicates very, very frequent reordering in the public cloud when you do not have any control.
Yeah, that's larger than I thought it would be. That's very interesting. Cool. Yeah. So just to continue the quick recap there, we also have the speculative execution. So we don't have to kind of have this sort of like commit latency waiting for the leader to sort of do everything. And then the last thing is we have this stateless proxy design, which allows us to offload multicast and quorum check and all that to some sort of middleware. So again, we're offloading stuff from the leader. Awesome. Cool. Great. Cool. So let's dig into the details a little bit more. So let's start off with deadline ordered multicast. Tell us more about it. Yeah. Explain it to us.
Yeah. As I have mentioned that the message reordering is a performance killer to the consensus protocols. So that is why we developed the deadline order multicast, or simply we can call that DOM. We developed DOM primitive to help us reduce the message reordering in the public cloud. So the design of DOM primitive is quite simple. So suppose that we have multiple senders and we have multiple receivers, and the senders will multicast the messages to the receivers. We hope that the receivers can receive the same sequence of messages. So in order to do that, first, we synchronize the clocks of the senders and receivers. So with the clock synchronization, the sender we can measure the one-way delay between the sender and the receivers. So in that way, when the sender wants to multicast the messages, it will attach a deadline on the messages. So the deadline is decided by the sending time plus the maximum estimated one-way delay between the sender and all the receivers. So in the good case, in most cases, when the request is multicast, it should be enabled to arrive at each receiver before its deadline. So in that way, after receiving the messages, the receiver will just hold the message until its deadline, and then it will append this message to the log list. So we can imagine that if the DOM can eliminate all the message reordering, then each receiver should establish an ordered log list which follows the increasing order of their deadlines. So in that way, we can achieve the consistency among these receivers. But we should also notice that the DOM primitive is just a best effort primitive. That means we are trying our best to reduce the message reordering, but we do not guarantee that we can eliminate all the reordering. So that is why for Nezha, we should have a fast path to commit a request efficiently if the message reordering is completely eliminated. If the message reordering is completely eliminated, but if the message reordering still occurs, it can still lead to inconsistency. So in that way, we still need to have a slow path in Nezha protocol to resolve the inconsistency and finally commit a request.
Awesome, cool. So I'm just trying to kind of get my head around the idea of the DOM primitive then. So I guess the deadline is every time we want to send a message, the clocks are synced. So I kind of say, okay, I guess the parameter that you control there is how long you set the deadline to be, right? I guess that's something you can manually control. Like, is that sort of configurable? Like, how do you know from how long to set the deadline for, basically?
Yeah. We decide deadline in this way. So as I mentioned, we have the clock synchronization. So in that way, so periodically we will send some probing packet from the sender to every receiver. So in the probing packet, we include the sending time, and when the receiver receives the probing packet, it can calculate how long does it take for the probing packet to arrive at the receiver. So that is what we call one-way delay between the sender and the receiver. And by collecting these one-way delay samples, we can make an estimation of the one-way delay between the sender and receivers. So for example, if you have 3 receivers and sender sends the probing packet to these 3 receivers, but between the receiver 1 and the sender, maybe the one-way delay is 20 microseconds. And between the sender and the receiver 2, it is maybe 40 microseconds. and between it with stream, it may be 30 microseconds. So since we have known these one-way delays between the sender and receivers, so when the sender wants to multicast the messages, it will use the sending time plus the max of the one-way delays. So that should be sending time plus 40 microseconds. And that will be the deadline for to multicast this message. So in the good case, this message should be able to arrive at all the receivers before the deadline. And then if it arrives early, then the receiver will hold the message until its deadline, which means the receiver will just check its clock time. And then when the clock time passed the deadline, it will release the request and append it to the log list.
Fantastic. I'm really excited to kind of hear some numbers on this later on, but cool. So before we jump to that, we need to get through the fast path and the slow path. Yeah. But maybe before we even do that, we should maybe talk through the architecture of Nether a little bit more and some of the assumptions that you've made while you were designing this protocol.
Yeah. So briefly speaking, I should say that the common setting, the setting of Nezha is quite similar to the setting of traditional protocols. So we still have 2f+1 replicas. So typically you can have 3 replicas, 5 replicas. You can have an odd number of replicas. And among these 2f+1 replicas, 1 replica is elected as a leader, and the other replicas are followers. So when the client wants to commit its request, it directly talks to one proxy, and the proxy will do the request multicast, and later it will also do the quorum check to decide whether this request is committed. And if the request is committed, it will return the execution result to the client. And here, as I mentioned, with the DOM primitive, we have a fast path. If there is no message reordering, then this request should be committed in the fast path. But if there is message reordering, it can lead to the inconsistency among replicas. But that is not a big worry because proxy will detect the inconsistency. And then finally, the replicas can commit the request in the slow path.
Amazing stuff. So let's go through the fast path then. So walk us through the fast path, the happy case where we've not got many messages out of order. The DOM primitives work perfectly. Cool. Yeah. Take it away.
Yeah. For the fast path, it works in this way. So the proxy receives this message and receives the request from the client. And so it uses the DOM to multicast the request to all the replicas. In the happy case, we do not have message reordering. So in that way, every replica will receive the request and hold the request until its deadline. And then this request is released and appended to the log list of this replica. So here we have a smart design. So that only the leader will execute the request following the increasing order of their deadline. But the followers do not execute the request. So followers only need to maintain the log list. And then every replica will send a reply to the proxy. And we call this reply fast reply. So inside the fast reply, every replica will include a hash value. And this hash value represents the log list on this replica. So after receiving the fast replies, the proxy can check the hash value inside the fast replies. So in that way, it can know whether these replicas have consistent states. So if the proxy receives the fast reply from the leader and also receives the fast reply from f plus half f followers, then this request is considered committed in the fast path. And because the leader's fast reply will include the execution result, so the proxy will obtain the execution result and reply to the client. So this is the fast path.
Nice, cool. So I guess now we've got the fast path, we need the slow path, right? So what happens when things are out of order and we can't take this speedy route, we can't take the shortcuts, we've got to go the long way around? How does that work?
Yeah, cool. So as you have mentioned that this is the fast path is just about the happy case. So we cannot guarantee that every request can arrive before its deadline. Let's see if some requests arrive very late and it arrives at some replicas after the deadline. Then the replica receives this request. It tries to append this request to the log list, but suddenly the replica notices, oh, I have already appended a request with a larger deadline, so I cannot continue to append this incoming one because this guy has smaller deadline. If I appended that will violate the increasing order of deadline of my log list. So how should we address that? So for the leader replica and the follower replicas, they will take different actions. So for the leader replica, we gave them much power. So if the leader replica finds that, okay, this incoming request deadline is too small, then the leader replica will modify the deadline of the incoming request to be a larger value. And then this request becomes eligible to be appended to the log list of the leader. But for the follower replicas, they do not have so much power. So when the follower notices, okay, this guy, the incoming request deadline is too small, we cannot append that. The follower will just put the request aside. It will not handle that at this moment. So in that way, you can see if some request is appended, but if the request is appended to some replicas, but not appended on the other replicas, then these replicas will have inconsistency. So in that way, they will generate different hash values in the fast replies. Then the proxy will detect this inconsistency. So the proxy will not be able to commit this request in the fast path. So here we make the leader replica take an active role. So that means every time the leader appends the request into a log list, the leader will also broadcast its log indexes into the other follower replicas. So after the followers receive the log indexes from the leader, the followers will listen to the leader. It will say, it may notice that, okay, my log list is inconsistent with the leader. So I must modify my log list to keep consistent with the leader. So here, I hope you still remember when I was describing the fast path, I'm saying that only the leader will execute the request. Followers only maintain the log list. So this is quite useful in resolving the inconsistency between the leader and followers. So imagine that if we also ask the followers to execute the request at the beginning, then when we are trying to resolving the inconsistency, maybe we will need to roll back at the follower. So that can be quite expensive and even unsupported by the application. But in our case, the followers do not execute the request. So to resolve the inconsistency, the followers just need to modify the log list, and then it can rapidly fix the inconsistency and keep consistent log list as a leader. So after the followers have completed the resolving of the inconsistency, it will send another reply to the proxy, which we call that slow reply. And the proxy, after it receives the fast reply from the leader and also the slow reply from F followers, it will consider this request committed in the slow path. And again, it can obtain the execution result from the leader's fast reply and reply that to the client.
Fantastic. So I'm really interested to see how kind of the performance numbers behind the fast path versus the slow path versus other protocols out there. So I think it's time to talk some numbers. Can you tell us about your experiments and your setup and what sort of benchmarks you ran and what you compared Nezha against?
Yeah. Actually, we have compared the Nezha protocol with multiple baselines, including, I remember it is about 6 to 7 baselines, including MultiPaxos, FastPaxos, NOPaxos, Raft, and ePaxos, Domino, and so on. So at the very beginning, we only conducted now evaluation in the local area network. So we just employ the VMs in Google Cloud. So we run the comparative evaluation in single data region. And we have achieved much higher throughput and better latency. So the speed up can be about 1.3 to 20.9x compared with the baselines. But later, when we submit to the VLDB, we got some feedback from the reviewers. And reviewers suggest that we should also do some evaluation in the wide area network with multiple regions. And then when we supplement the evaluation in the wide area network, actually the performance advantage of Nezha becomes even more distinct. Because we have known that in the wide area network, perhaps the most well-known protocol is ePaxos. ePaxos claims that it can achieve optimal latency in the wide area network. But that assumption will become not true when we separate the client and the replicas into different regions. So in the more general setting, when we have different regions for the client and the replicas, only Nezha protocol can achieve the optimal latency, which means we can commit the request in just one RTT in the fast path. For ePaxos and MultiPaxos, they still need at least 2 or even 2.5 one RTTs to commit the request. So that makes our latency performance much more distinct compared with the baselines.
Yeah, for sure. I mean, like one round trip versus 2.5, that's a big difference.
Yeah, sure. Yeah.
Cool. So I guess kind of on this then, so this works well when obviously when the DOM perimeter is working great and our messages aren't kind of being reordered. Did you do any experiments sort of in the extremes of what happens when kind of, well, I don't know, what is the performance sort of tipping point when I'm seeing a lot more of my messages being arriving sort of out of order and I need to do some reordering? So I end up on the slow path more than I do on the fast path.
Yeah, actually, I think actually we have included such experiment in our conference paper, in our conference version. So for the DOM, the big for DOM, the key parameter that we need to care about is how should we decide the estimated deadline. So here we are using the sliding window to estimate the one-way delay, and further we can decide the deadline. So for the sliding window, we have maintained a hyperparameter which is called the percentile. So that means you collect some OWD, some one-way delay samples, and then you will just choose maybe to the 50 percentile, to the 75 percentile as the estimated one-way delay. Of course, the larger percentile you use, then you will suffer from longer holding delay. But in that way, you can reduce more message reordering. So we have chosen different percentiles used to estimate the one-way delay and further decide the deadline. And finally, we found that with the 50 percentile, we can achieve the best trade-off between the holding delay and the faster commit ratio. As we increase the deadline value, then of course we can continue to increase the fast pass ratio. We can continue to increase the fast commit ratio, but that increase is just marginal. We are just suffering from more holding delays, which causes longer latency. So in our future work, we need to do more experiment to maybe we will develop an automatic mechanism to select the estimation method. But in our current design, we have used the sliding window estimation with the 15 percentile as the estimated value. That has been proved to achieve the best trade-off.
Yeah, I guess that probably is going to be the best answer in most cases, right? So for now, it's good. But it's interesting, like as a future research direction, sort of kind of having this monitored at sort of like at runtime and varied depending on what's happening in the underlying network or whatever, and sort of changing it over time based on various factors. That'd be really cool to see that. Awesome. Yeah, I guess sort of like building on top of this then, so are there any sort of, I mean, I always like to, I always kind of ask this question, but are there any sort of scenarios in which Nether is sort of suboptimal in terms of its performance? Like what are the areas where it's sort of, its limitations, I guess?
Yeah. For the limitations, actually, we should actually admit it has limitations. And also, I have uploaded the technical report of Nezha to archive. So in the appendix, I have talked about the limitations. I think the biggest limitation is still about the clock synchronization. As I have mentioned, actually, I should emphasize that Nezha's protocol's correctness does not depend on the clock synchronization. So we only rely on clock synchronization for performance rather than correctness. But so even the clock synchronization fails, the protocol is still correct, but the performance will suffer from some negative impact. So for example, if the clock synchronization suddenly fails, and then the DOM primitive the DOM primitive is likely to generate very large deadlines. And when the receiver receives when the replica receives the message with very large deadlines, and then this replica will just hold the message for a very long time. And this long holding time will be counted into the commit latency of this request. So in that way, that will lead to very bad latency performance. So, and in the appendix of the technical report, I have discussed this issue and also discussed some mechanism to address this problem. For example, when we have noticed that the holding time very long, we can force this request to be committed in a slow path. So in that way, we do not need to suffer from the long holding time caused by the wrong deadline. And here I want to highlight one thing, that is, for this kind of issue, it can be theoretically it can be a problem, but in practical cases, it can hardly happen. I said this because of two reasons. The first reason is because of the Huygens algorithm we used in Nezha. So Huygens is a very robust clock synchronization algorithm, which means that it is using a robust probing mesh. So even some clock synchronization agents fails. So long as there is no Byzantine node, the remaining healthy nodes can still synchronize with each other, and they can quickly converge to the synchronized clocks. So the second reason is, even if there is some Byzantine node which keeps polluting the clock synchronization, in the recent literature, I have noticed that there are some mechanisms developed. For example, you can use some watchdog mechanism, and the watchdog mechanism can detect the Byzantine node. And then if this node keeps polluting my clock synchronization, we can just detect that and kick that node out of the synchronization scope. So in that way, these mechanisms will prevent the long-lasting negative impact from Byzantine nodes.
Fascinating stuff. Yeah, it's interesting to see. I mean, I'm a little bit sort of detached from the whole sort of Byzantine sort of them sort of protocols, BFT protocols, and sort of I don't keep up to speed with them too much. So it's really interesting to see that they're kind of in their way even working on solutions around that sort of, and like it's like a watchdog or whatever, and how that can be leveraged for these sorts of protocols as well, which don't have the same sort of underlying assumptions. Yeah. It's really cool. I had another question as well about how do you handle sort of changing the member set of the protocol, like rolling in new members and rolling out old members. How does Nezha handle that?
Oh, the short answer is for now we just inherited the view based approach. We will just use the view stem replica approach. But in the near future, I think we can design more efficient membership change. For example, in the recent protocol, maybe you have noticed which is called Matchmaker. I think it is also published in VLDB. So for the Matchmaker, it can achieve even more efficient reconfiguration. And I believe such protocol can be adapted and be applied to support the membership management in the future version of Nezha.
Fantastic stuff. So I guess kind of leading on from that then, where do you go next with Nezha? What's the next thing on the research agenda?
Yeah, good question. So actually, this is not the end of the story of Nezha. So currently in my research, there are 3 ongoing directions related to Nezha. So the first direction is productize the Nezha protocol. So after the Nezha protocol is developed, my supervisors and I all believe that this Nezha protocol can become a promising alternative and replacement of the legacy protocols such as Raft and MultiPaxos. So for now, currently I'm working with some industry colleagues, and we are trying to refactor the code base of Nezha protocol. And after we have done that, we will continue to integrate Nezha into some industry systems. For example, Kubernetes. Currently the Kubernetes is using the etcd as the storage backend, and etcd actually is a standard implementation of Raft. And based on the feedback from some industry staff, they told us that the Kubernetes is suffering from the performance bottleneck due to the etcd backend. So if we can replace the etcd with the Nezha protocol, which offers higher performance, then we should be able to bring performance boost to the Kubernetes system. And similar systems such as the Apache Parser, which is now using the Zookeeper, and Apache Parser is also suffering from the bottleneck due to the Zookeeper. And in the future, maybe we can also replace the Zookeeper with Nezha to bring more performance improvement for Parser. And another scenario is the financial system. For financial systems, they also require the fault tolerance. So this is something related to my first project, which is called CloudX. And in the future, I think I will also apply the Nezha protocol to my first project to provide the fault tolerance for the financial system. So this is the first direction in my schedule. And the second direction related to Nezha is to extend the application scope from the consensus protocol to concurrency control protocol. Oh, by the way, I have listened to your podcast published last month when you are talking about the DTalk project with Coin. So that is a very insightful podcast, and I enjoyed that a lot. So, based on my understanding, you see, the concurrency control protocol actually is trying to establish the ordering agreement of multiple shards. So that means you submit a transaction. This transaction will be executed across multiple shards, but we need to satisfy the strict serializability. So concurrency control protocol is trying to establish ordering agreement across multiple shards, while the consensus protocol is trying to establish the ordering agreement across multiple replicas. So these two share much similarity. So if we can do high-performance consensus protocol with clock sync, then we should also be able to do high-performance concurrency control with clock sync. So actually, currently, I'm already implementing such a new protocol, which can provide both consensus and concurrency control. Nowadays, I have completed the design of the new protocol, and I'm now involved in implementing and evaluating. So hopefully, I think this new protocol will come out very soon in the near future. And maybe when that day comes, we can have another talk about the new protocol. And this is the second direction. And for the third direction, as you have mentioned, I'm also looking at some literature on the Byzantine fault-tolerant scenario. So Nezha, at this moment, Nezha is just a crash fault-tolerant consensus protocol. So compared with the CFT consensus, the BFT consensus is even more challenging, because in the BFT consensus, we should not handle the case when the node fails. You should also handle the case that the node is dishonest. So how should we achieve high-performance BFT consensus protocol? And in the past 3 years, we have seen that many researchers are becoming more interested in using TEE to accelerate BFT. So TEE stands for trustworthy execution environment. For example, Intel SGX is a very good TEE technique. So I'm thinking that by using the TEE technique and combine the TEE technique with Nezha protocol, we can make Nezha work. We can also make Nezha work in the BFT scenarios. So that is the 3 dimensions.
Fascinating. I mean, you're going to be busy for a long time, and that sounds fascinating that directions. I'm really excited. I mean, if you can my next question is going to be, what impact do you think your work can have? But I mean, if you manage to get Nezha in using Kubernetes and using Apache Pulsar, and then obviously the financial application, that'd be some fantastic industry impact, right? That'd be amazing.
Yeah, exactly.
And yes, you can definitely come on the show again and talk about the extension to concurrency control protocol. That'd be a fascinating chat, I'm sure.
Yeah, sure.
And and the third direction as well, the BFT, that seems fascinating as well. So yeah, I'm sure there's going to be loads of really interesting work coming out from yourself, from your lab over the next over the coming years for sure. So cool. So I mean, I guess sort of my next question was going to be, what impact do you think your work can have? But I don't know if you want to add anything more onto that, like how do you think people can leverage your findings in their day-to-day sort of work?
Yeah, as we have mentioned in the previous question, I think that by replacing the legacy protocols with Nezha, we can bring the performance improvement to many distributed systems. And another thing which is also put in my to-do list, maybe in the far future, that is, for the DOM primitive, we think that we can make the DOM primitive as a general middleware. So if we can make the DOM as a general middleware, we can plug into any distributed systems which requires consistency. So in that way, it should be able to bring a general acceleration to the distributed systems. So that can also be a promising direction that we need to do. But of course, by implementing this general middleware, it may be more challenging. We need to consider many other issues.
I find that'd be really interesting, yeah, for sure. I guess, So of course, my kind of just changing direction a little bit here. Be sort of working on the Nether project. What's the most interesting thing that you've learned?
Actually, yeah, I think for the interesting thing, I want to share two lessons I learned. One good news and one one bad news.
Okay.
So let's first talk about the bad news.
Yes. Okay.
Yeah. So first, let's talk about the bad news. So in the distributed while I was doing the research on the consensus protocols, I realized that this area is really crowded. So, for example, because consensus protocols have been developed for more than 30 years. So there are too many smart people, and they have spent too much effort in developing different kinds of protocols. So this is what I call history burden, because we are doing that 30 years after after the pioneers. So when we develop a new protocol, in order to make our protocol stand out, we need to defeat many baselines. This is what we have encountered from the reviewer feedback. So when we submitted the Nezha paper to some conference tracks, and the reviewers were just argue that why don't you compare with baseline A? Why don't you compare with baseline B? So in order to satisfy the reviewers, we need to add more and more evaluation in order to distinguish our protocol compared with the existing works. So for the young researchers and students who want to enter this area and make some contributions in the consensus protocols, I suggest that you must be prepared for the laborious implementation and evaluation work that you need to do. So this is bad news, and but there are also some good news. So the good news is we should be aware that compared with the young researchers 30 years ago, we are now enjoying much better implementation conditions. You can have many available powerful techniques that you can use to improve the protocols. So if you want to make a contribution in the consensus protocol, I'm sure that you can do something. Based on my understanding, there are two paths that you can consider. So the first path is that you can consider to use some special network support, like what NOPaxos and Speculative Paxos have done. You can also use RDMA, use program switch, use SDN. You can use these new techniques to enhance the performance of the consensus protocols and build your own contribution. And the second path is to use some software and deployable technique, such as the clock synchronization and such as TEE. By the way, TEE is also available in the public cloud like AWS and Microsoft. So by using these new techniques, you can create the unique contribution which you can do, but the early researchers cannot do. So in that way, you can make your work stand out.
I think that's a fantastic answer to that question.
Yeah.
That's great. I love that. I love the bad news and I love the good news as well. I say it's great stuff. But it's so true, that kind of the history bed, and it's true. Obviously, I've spent a lot of time in the same sort of field and with database research. It feels like everyone's already done it all in the 60s and 70s and 80s, right? So there's so much to sort of learn and kind of get your head around before you can then make some sort of like layer on top, right? And make some incremental improvement in some area. But yeah, no, I guess that's the way the world is at the moment, I guess. But anyway, cool. Awesome. So yeah, I guess kind of on the other side then, were there some sort of things that you tried while you were working on there that failed that maybe the listener might be interested in knowing about?
Yeah. I think this question is quite relevant to the previous question.
Yeah.
I think the problem is that in the research, actually this is a common issue for almost all the system related research. That is, you must behind the paper, you need to spend much more effort trying to do the implementation and evaluation. Actually, Nezha protocol has been submitted for 3 times, and it is accepted in the 3rd time. But for the first 2 times, we submitted to the other conference venues, and it is rejected. And the reason for the rejection is because they said that, okay, we do not compare with the other baselines, or we do not do this experiment or that experiment. So, this actually makes me quite disappointed because we have designed such protocol. But the problem is we need to make now protocol defeat so many rivals.
Yeah.
So that is, but this hard work cannot be reflected in the paper. So that is quite disappointed. So when I got rejection for the first and the second time, my supervisors come to comfort me. They said, "Oh, Jinkun, do not be so disappointed. For the Raft paper, they have been rejected for 6 times." So
really, okay, well, yeah, that makes it easier now, right? Knowing that they got rejected 6 times, and look how influential that protocol is.
Yeah.
So, yeah.
So finally, so my supervisors already encouraged me. He said that we believe that our work is a good work, so we just need to keep working on that, and it is just a matter of time to get it published. And finally, yes, we get published in the VLDB, and also the reviewer and the final review feedback is very positive. That encourages us a lot.
That's great. But it is kind of quite disheartening, right? That you've got to do so much sort of work that doesn't ever get any real credit in the paper, right? Like, and it's like, I don't know, maybe it's a problem. It's a kind of a systemic problem with the system at the moment, I guess, with the academic system and the way that things kind of work. And I think it's especially prevalent in systems research. But at least it got accepted eventually, and I'm glad it did get accepted because it was a great read. Cool. So we've got just a couple more questions now, and this one is can you maybe spend some time telling the listener about your other research? I'm sure you work on loads of interesting things or haven't in the past. So tell us a bit about some of your other stuff.
Actually, I want to share some lessons, some tips that I have learned based on my past research experience.
Yeah, go for it.
Yeah. I think for the PhD students, this is a common challenge that we will encounter. So how should you find the project that you think is promising and what you think you can do? So I think for the PhD research, it can be divided into 2 steps. Step 1, you need to have an idea. You should have an idea that you believe it is promising. The second, step 2, you need to implement your idea and demonstrate the effectiveness of your idea. So comparing these 2 steps, I think step 1 is harder. Because because this is the starting point. If you do not have the idea, you will just be blocked. You cannot make any progress. So here I want to share the experience. How should we generate some interesting ideas? So there are 2 ways. The first way is if you do not have the idea, I think at least you will have a general direction. For example, you can ask your supervisor to give you a general direction. Of course, the supervisor will not tell you what to do step by step. That is your responsibility to figure out what to do step by step. So how should we, after we have got a general research directions, you will need to do a lot of literature review. For example, when I first decided to do something in the consensus protocol, I just need to read about 20 papers, which published in the top tier conferences. So after you have read 20 papers, I believe that you should already get some sense. You should already have some inspiration. If you are saying that, okay, after I have read 20 papers, I still have no idea, then don't worry. Keep going and continue to read another 20 papers. And keep doing this. Finally, you will find something interesting. This is the first option that I suggested to other PhDs. And the second option is to make your hands dirty. For example, if you do not know what to do, you can find a merge system. For example, if you want to do something in the consensus protocol, you do not know what to create, then you can start by implementing the Paxos protocol or by implementing the view stem replication protocol by yourself. So when you are doing the implementation, you will learn some potential bottlenecks, some potential issues that the other guys cannot know if they do not implement that. So based on that, perhaps at the beginning, you will have a very small idea, and then you continue with your small idea. During the implementation, you will make your idea bigger and bigger, and finally, probably you will have a good work. So that is the second tip I want to share with the other PhD students.
That's fantastic. Honestly, I love that. It's great. I think that's fantastic advice is read, keep reading. And it's a great way to generate ideas, right? Like that was sort of the approach that I sort of took initially and was sort of like, if I can read all of these distributed transaction papers, then surely maybe one day I can have an idea of my own. And then obviously, get your hands dirty, right? And I think that kind of advice is true in life as well, in general, in all things, right? Like you kind of, you've got to, I think they say you've got to crack a few eggs to make an omelet, right? So like you've got to get your hands dirty, get in there, and then ideas flow from there, right? And the first thing you do might be terrible, but everything is at first, right? The first podcast I recorded was terrible, and hopefully by now they've got a little bit better. I don't know. The listener can be the judge of that. No, I'm joking. But but no, I think that's brilliant. So I think that answers that sort of. I normally ask about people's creative process, but you've kind of answered it there as well. So I think that's a really, really cool sort of answer. I really enjoyed that. And I guess, just the time for the last question now is, what's the one thing you want the listeners to take away from this podcast today?
To summarize in one sentence, I would say clock sync is becoming the new powerful weapon that we can use to accelerate the distributed protocols. That is what I want to share with the audience.
That's fantastic. Great. Let's end it there. Thank you so much, Jinkun, for coming on the show. It's been a fascinating chat. I've loved it. If the listener wants to know more about Jinkun's work, we'll put links to everything in the show notes. And again, if you do enjoy the show, please do consider supporting us through Buy Me a Coffee. It really helps us to keep making the show. And we'll see you all next time for some more awesome computer science research.